The just-in-time compiler, commonly known as the JIT compiler, is one of the most critical components of the Common Language Runtime, CLR. It plays a central role in the execution of .NET applications by converting intermediate language, IL code into native machine code. Without the JIT compiler, Illinois code generated by .NET language compilers could not be executed by the CPU. The JIT acts as the bridge between platform-independent IL and platform-specific machine instructions. When developers write applications in C#, VB.NET, or other .NET-supported languages, the source code is compiled into IL rather than machine code. This design allows .NET applications to remain platform-independent. However, CPUs cannot execute IL directly. At runtime, the JIT compiler translates IL into native instructions that match the architecture of the system, such as x86, x64, or ARM. The main purpose of the JIT compiler is to perform compilation at runtime rather than at build time. This approach provides flexibility and allows the runtime to optimize code based on the actual execution environment. Unlike traditional ahead-of-time compilation, JIT compilation enables the runtime to generate highly optimized machine code tailored to the specific CPU and execution patterns. The JIT compiler operates on a method-by-method basis. When a .NET application starts, none of the IL code has been compiled into native code. As soon as the program calls a method for the first time, the CLR checks whether native code for that method already exists. If not, the CLR invokes the JIT compiler and passes the IL instructions of that method for compilation. Once the JIT compiler generates native machine code, the compiled code is stored in memory. Subsequent calls to the same method reuse the already compiled native code. This ensures that JIT compilation occurs only once per method during the application's lifetime, improving performance. This approach is known as lazy compilation. Instead of compiling the entire application up front, only the executed portions are compiled. This reduces startup time and memory usage, especially for large applications where many methods may never be called. One of the key strengths of the JIT compiler is its ability to generate CPU-specific code. Because compilation happens at runtime, the JIT can detect the exact processor features available, such as instruction sets and optimization capabilities. It can then produce machine code that takes advantage of those features, resulting in better performance than generic pre-compiled code. The JIT compiler also performs various optimizations. These include method inlining, loop unrolling, constant folding, dead code elimination, and register allocation. These optimizations significantly improve execution speed while still preserving correctness. In modern .NET implementations, the JIT compiler uses tiered compilation. Tiered compilation is a two-phase optimization strategy. When a method is executed for the first time, it is compiled quickly using minimal optimization. This ensures fast application startup. If the runtime detects that a method is executed frequently, it recompiles that method later using more aggressive optimizations. This dynamic optimization model allows applications to start quickly and gradually become faster over time. It combines the benefits of fast startup and high-performance execution. The JIT compiler works closely with the CLR's execution engine. The runtime provides metadata and type information to the JIT, allowing it to generate correct and type-safe machine code. Because IL is strongly typed, the JIT can make assumptions that are not possible in unmanaged environments. Another important aspect of JIT compilation is security. Before IL is compiled, the CLR verifies it for type safety. This verification ensures that the IL code cannot perform illegal operations such as accessing invalid memory or violating type rules. The JIT relies on this verification to safely generate native code. The JIT compiler also respects runtime services such as garbage collection. It generates code that cooperates with the garbage collector by inserting safe points where garbage collection can occur. This coordination allows the GC to suspend execution safely and move objects in memory when necessary. Memory management awareness is a critical feature of the JIT. The generated machine code includes metadata that helps the garbage collector track object references accurately. This ensures that live objects are not mistakenly collected. The JIT compiler also handles exception handling. It generates native code that supports structured exception handling. This allows the CLR to correctly unwind the stack and execute finally blocks during exceptions. Different types of JIT compilation exist within the .NET ecosystem. The most common is the normal JIT, which compiles methods as they are executed. Another approach is pre-JIT compilation, historically implemented through tools such as NGen. In this approach, Illinois code is compiled into native code before execution. Modern .NET also supports ready-to-run images. These contain precompiled native code to improve startup performance while still allowing fallback to JIT compilation if needed. Even in these scenarios, the JIT remains essential because it handles cases where precompiled code is not available or needs optimization. The JIT compiler also plays an important role in debugging. Debug builds use different JIT optimization levels to preserve debugging information. Release builds enable aggressive optimizations for performance. The JIT compiler adapts its behavior depending on the build configuration. In debug mode, it generates code that is easier to debug. In release mode, it focuses on speed and efficiency. One of the advantages of JIT compilation is version resilience. Because compilation happens at runtime, applications compiled years ago can still run efficiently on modern hardware. The JIT automatically takes advantage of newer CPUs without requiring recompilation of the application. This forward compatibility is a major strength of the .NET runtime. The JIT compiler also contributes to cross-platform execution. The same IL code can be executed on different operating systems and architectures. Each platform uses its own JIT implementation to generate native code suitable for that environment. This design is what allows .NET applications to run on Windows, Linux, and Mac OS without changing the source code. From a performance perspective, JIT compilation is often misunderstood as slow. While there is a small compilation cost during the first execution of a method, this cost is usually negligible in long-running applications. The benefits of runtime optimization often outweigh the initial overhead. In real-world scenarios such as web servers, background services, and enterprise applications, JIT-optimized code often performs extremely well. The JIT compiler also enables runtime profiling. By observing execution patterns, the runtime can make informed optimization decisions. This dynamic behavior is not possible with traditional ahead-of-time compilation. Understanding the JIT compiler helps developers write better code. For example, understanding method inlining and allocation patterns can help improve performance and reduce overhead. The JIT compiler is not a standalone component. It works as part of a larger execution pipeline. It collaborates with metadata, CTS, garbage collection, and thread management to ensure correct execution.